All right, let's jump right into this explainer. Today we are looking at how to make the massive leap from building simple Python games to manipulating giant professional-grade datasets. If you know Python, you already know how fun interactive scripts can be. But to handle serious data, well, we're going to need a serious upgrade to our toolkit. So let's dive into exactly how we transition from standard object-oriented programming to analyzing tens of thousands of data points in literal milliseconds.
Here's our quick roadmap for the day. We're covering Python's limits, meeting pandas, exploring core structures, slicing data, advanced filtering, and finally, loading up real-world data. Starting off with Section 1, Python's limits, why it's great for games, but kind of slow for big data.
Standard Python is an absolutely fantastic training ground. It's incredibly powerful for building interactive, command-line games using abstract classes and inheritance. And as a quick aside, when you're writing that code, always remember to use type hinting. It literally saves you from massive debugging headaches down the line and makes your code look super professional. But even with perfect type hinting, standard Python still has its structural limits.
So here's the million-dollar question, right? What happens when your pure Python loops hit a massive wall of data? Imagine your simple number guesser game suddenly goes viral, and boom, you have 50,000 user scores sitting in a file. If you try to run standard Python for loops to find the average score, your program is going to severely slow down. Pure Python just wasn't built for high-speed, parallel data processing out of the box.
Which brings us to Section 2. Meet Pandas, the absolute data hero.
Basically, Pandas is like an Excel spreadsheet on steroids. It's an open-source library that lets us process tabular data incredibly fast. Think of any structured data with rows and columns, like a CSV file. Pandas gives you the superpower to ingest that data, clean up all the messy missing values, and prepare it for AI models or visual analysis. This whole process, extract, transform, load, or ETL, is the backbone of modern data science. And Pandas, it's the gold standard for getting it done.
And just to put that speed into perspective, the open source community took it even further. NVIDIA created a variant of Pandas called cuDF that runs directly on your graphics card. Get this, it can be up to 600 times faster for massive data sets. 600 times. That means a data processing job that usually takes 10 whole minutes on a standard CPU could take about 1 single second. That mind-blowing level of optimization is exactly why learning Pandas is completely non-negotiable if you want to work with real data.
Moving right along to Section 3, core structures, specifically series and data frames.
Let's break down the anatomy here. A series is your foundational building block. Think of it as just a single 1D array, representing one single row or one single column of data. It behaves a lot like a standard Python list, but with one major superpower: the index. Instead of just accessing items by counting 0, 1, 2, a series actually lets you attach custom labels to your data points. Now, when you take multiple series and mash them together, you get a data frame. If a series is a single column, the data frame is the entire spreadsheet. This two-dimensional table aligns all your different series by their shared index. So you can have one column for names, one for ages, and one for salaries, and the data frame perfectly maintains the relationship between every single one of them. Notice how an index can use custom labels like A, B, and C instead of just the default numbers. That is the magic of Pandas in action. When you wrap a standard Python dictionary in the pd.dataframe function, it instantly formats it into this highly readable, easily manipulatable table structure.
All right, Section 4, slicing data. Lock versus illoc.
Let's clear up what is probably the absolute most common beginner confusion out there: .loc versus .iloc. If you want to grab data by its explicit label, like row A, you use .loc, and because it uses labels, asking for A to C brings you A, B, and C. It actually includes the endpoint. But .iloc, that acts just like a traditional Python list. It uses integers, and if you ask for 0 to 2, it excludes that final number, giving you just 0 and 1. Getting this straight early on is a total game changer.
And what if you have data you just don't need? Say we want to completely ditch the salary column. You simply use the df.drop method, pass in the column name, and set axis equals 1 to tell Pandas you mean a vertical column, not a row. And just like that, the noise is gone. You've got a fresh, streamlined data frame ready to go.
Now for Section 5, Advanced Filtering, filtering like a pro.
Dropping columns is easy, but finding highly specific rows requires a bit more finesse.
Imagine we've got this raw data set, and our goal is to find young, high-earning employees for a targeted campaign. Doing this in standard Python would mean manually iterating through every single row, one by one.
But in Pandas, we literally just apply a Boolean condition. It's exactly like standard Python logic. By using an ampersand, we're telling Pandas to evaluate the entire dataset simultaneously. Show us where the age is less than 30 and the salary is over 60,000.
And boom, instantly, Pandas filters our massive table down to exactly the matching records. John and Emma are out, and we're left with just Alex and Lisa. And because this is vectorized under the hood, this filtering happens at lightning speed, even if you were dealing with millions of rows. You can even chain this kind of thing with .lock to graph specific columns based on a text condition. Let's say you only want people who live in New York. You pass in your condition, city equals New York, and then tell .lock you only want to extract the name and city columns for those exact matches.
And there you have it. Perfectly clean, incredibly targeted data, all done in one single line of code. We stripped away everything but the exact data points we needed. This is exactly how you prep datasets for machine learning.
Finally, Section 6, Loading Real-World Data.
Getting your data from the wild into Pandas is basically a super simple three-step pipeline. Whether your data is in a CSV, a nested JSON payload, or scraped from an HTML table, Pandas has a dedicated read function for it. You just feed it the file path, and it handles all the messy parsing for you automatically.
But once you've actually got that data loaded, please, whatever you do, don't fly blind. Always run these 4 crucial inspection methods. Use .head to visually check your top rows. Run .info to hunt down any missing or null values. Call .describe to instantly generate statistical summaries like your mean and max values. And check the .shape to see exactly how many rows and columns you're really dealing with. Think of these as the vital signs for your dataset's health.
We've successfully leveled up from looping through simple Python games to commanding massive data frames with absolute ease. The tools are incredibly powerful, but they're really just waiting for you to ask the right questions. So, knowing you can now parse millions of rows in literal milliseconds, what massive data problem are you going to tackle next? Keep exploring, and I'll catch you in the next explainer.